We're going to start talking some more about photon mapping and then continue with the participating medium, the sort of volume scattering. But since the method I'm going to propose for that is photon mapping, I wanted to do photon mapping first. And the idea is we send photons from the light sources into the scene. And every time they bounce on a diffuse surface, we save the location and the direction, maybe the color and power of the photon. So, start photons at the light sources. The bounce on surfaces and save location, direction. I should say incoming direction. And flux, which could include color. On diffuse surfaces. So it's like the first part of the bidirectional path tracing. And then eventually we'll gather the photons with rays from the eye. So you can think of just gathering the photon map means you've got, like the irradiance caching, you've got all these photons where they hit. So it's not an irradiance value that's there. It's actually a single photon that started from the light source. And if you could gather all those, you could render them. In fact, I guess the formula to add up their flux, so the photons are starting out at light sources. Let me put a light source on the ceiling of a room. Let's see, how does a room look? I guess there's the ceiling. Trying to see what would the ceiling look like. To us, the ceiling would look like something like this if we were from inside the room. That's the picture I couldn't think of drawing. But then this light source is up on the ceiling. Not thinking very well today. Here's a light source, and the photons are bouncing around on the walls of the room. And, here's the floor. And maybe we've got a table. I always like to draw a table in my room. And the photons are bouncing around. Every time they hit a diffuse surface, we save it. So we save it there. Save it there. And we're going to do some sort of Russian roulette, and we're going to bounce them according to the BRDF, and with the Russian roulette determined by the hemispherical reflectivity rho, so that the photons are really representing the density of the photons. So here's another surface where it hit, and say Russian roulette made it stop here. Then we generate another photon, and we keep going till we've got lots of photons on the surface. And then if we have a viewing ray, we could think of either gathering these photons directly in a region, or if that were too noisy, we could think of doing a gathering from the visibility point to look in all the other directions and then figure out what the density of photons were there. So the chief thing it was good for, and I mentioned it last time, was caustic maps. So if sitting on the table we have a glass sphere, we'll generate a lot of rays just aiming at the glass sphere and refracting through it and hit the table, and we'll only get the caustics, the specular reflection and refraction rays to make a separate caustic map. So we have, let's say, the caustic photon map for specular bounces. From the light. So I'm not going to worry about glossy. My surfaces are all going to be specular and diffuse. That's the way it's presented in the book and in the papers that the book came from. And so that gets all paths I guess L, S, plus D. And the paths stop at D where the photons are stored. And the reason I put plus is because we aimed these photons specifically at only the specular surfaces. So if we have a mirror on the wall, we can aim a bunch of photons directly at that mirror and get the exact reflected rays. And they're also, maybe the mirror is lighting up the wall and the floor with a spot of light that came from specular bounces. Or maybe it's lighting up this sphere, right? So the light, in addition to the light source, we have the image of the light source in the mirror reflecting through the sphere. And that would give us, another caustic over here. And then we have a global photon map. And that means we don't aim the photons in special locations. We aim them on any surface. So basically, we have any number of specular or diffuse reflections. But then each of them, every time it hits a diffuse surface, we're going to store the photon. So as I showed at first, it gets stored in many places. And that's for all the surfaces. So how are we going to do this? What we're going to do is we choose a random light source. L-I-G-H. And this is like when you were doing your, if you had multiple lights in the room and you were doing your direct illumination with probability proportional to its power. So that's, the power is, say, the radiosity if it's a diffuse emitting light source. I guess it should be BE, and say it's the kth light source, times the area. And if it's going to sum to 1, you've got to divide it by the total power emitted. PET is what they call it in the book. So that's the sum over all light sources of their radiosity times their area, which is the power. And then I'll continue on this board. I should have probably started on this board. Choose. This is for a diffuse emitting light source. We'll assume it's equal in all areas and directions. Point on the light source, GHT source, with probability, uniform probability. And so if it's a light source's area AK, 1 over AK is the density, right? So if we ask what's the probability of, maybe there's another light source up here somewhere, 2 smaller ones and a bigger one. What's the probability of getting a light source point on this light source? We'd have to multiply this by 1 over that. So on light source K, light K, so the total probability is the product of those two. One over AK times B emission K, AK, over the total emission power, what do they call it? PET. And so the AKs cancel, and you get the probability that's given in the book. And now, if it's a diffuse light source, choose the direction that it's leaving, say, proportional, why don't I call the direction theta? Proportional. Okay, it's got to be the standard for shortening weighting, right? Because we don't want them to leave equally in all directions. If it's equal radiance in all directions, I've got to leave less at a glancing angle because of the foreshortening factor. So it's proportional to cosine of the angle between theta and the normal of light source k. And the probability then is this over that, the integral of that, which is pi. So that's the probability density distribution that you're going to use to choose the random angle. We've done that for homework also. Okay, and then you shoot them out on the surface from the light source, and each time you hit, we've got the visibility and the geometric factor of the solid angle of this surface point already, and we're not picking random points on the surface, we're actually tracing the ray. So the solid angle gets the dA over r squared stuff for each bounce. And if you choose it, you can either choose it proportional to the product of the cosine distribution and the BRDF, which is what you need to have the rest of the geometric factor go away and have the photons all have constant energy. But sometimes that's complicated to sample. If you wanted to sample, say, cosine weighted and then multiply the power of the photon by the BRDF. Of course, if it's a diffuse surface, it's fine because it's uniform in all directions. The cosine times the hemispherical reflectivity is already the probability. So if the hemispherical reflectivity is in your Russian roulette, you can actually have all the photons keep constant energy. So it's like the light source end of the bidirectional ray tracing computation. You can organize it however you want. If you want to accumulate different flux, multiply the flux by the BRDF if it's something that's hard to sample. And then you save the directions as well as the locations in a spatial database. What the photon mapping idea was first published by Henrik von Jansen, and he suggested using balanced KD tree to store the photons. So it's like an octree, except it's a binary tree. It's first divided in X, and then in Y, and then in Z. And each time it's divided, you sort of divide it to put half of the photons on one side and half of the photons on the other side of your dividing plane. And then you just stop when you've got a certain number of photons, say 4 or something in the leaves, then you can call it a leaf. Otherwise, you keep dividing. So it's similar to an octree, but it's perhaps more efficient because the divisions are really adapted to where the photon distribution is. And so the way to do it is you first trace all the photons, save them in a huge list, and then, with these binary bisections, sort the list into octree, KG tree pieces. And then when you're done, you take this tree and reorganize it so it becomes a balanced tree. And that just is supposed to make the search for the photons in a given neighborhood easier. So one thing you could do actually is use a histogram method on an octree or a KD tree or just a cubical grid. You could say each KD cell, tree cell, octree cell, grid cell has a volume, and the flux density is just the flux, the number of photons that hit, or the sum of their fluxes if you've kept fluxes associated with them, divided by the area of the piece of the surface. You could do that, say, if you were storing them on surfaces. And so that's a histogram method. You know, we could do like a quad tree on every surface, or a grid on every surface, say parameterized grid like you'd use for texture mapping. So if you put it on surfaces, then you have the surface piece, and you have the area of each grid cell, and you could just divide the flux by the area and get the irradiance that way. Because the cosine theta part of the irradiance is also already taken care of, right, by the geometry of the ray tracing. But like Ward last time, it's more efficient to store them in a 3D data structure instead of a 2D data structure. First of all, you don't have to worry about meshing every one of the walls and floors and tabletops and chair pieces into some sort of parameterized surface that you can put little grid cells on. So it makes the meshing easier, and you know how you make the meshing can bias your answer, both for the if you store it in 3D, then if you have like this eraser near the edge of the blackboard, we get the photons around that were good for shading the wall and the eraser and the blackboard. They're all stored, and we can gather them all, and they give a good representation of the photon density. So if you put it in a 3D structure, then instead of counting how many are on each surface area, you'll count by gathering by a sphere. So to render a surface point, say X, what we'll do is we'll use, let's see if my notes tell me the name of it. Nearest neighbor, I think, is what the book called it. Take the smallest sphere around X that contains as many points as you need to specify in advance. Say n points. N could be like 50 or 100 or some number which would give you enough statistics that you wouldn't have too much variance. And that means that if you have a lot of photons, like an acoustic map, there are regions where the light is concentrated by the refraction or reflection. And so your spheres will be smaller there, which means you'll be able to get your high detail varying with position. Whereas if the photons are more spread out, so you couldn't notice the difference anyway, you'll have a larger sphere. And then since it's really on a surface, the area that you're going to assign to this surface, whichever surface you're rendering, is pi r squared. Sphere, why don't we say the sphere of radius r. And so here I'm going to write the formula in the book, the way they wrote it. L, X, omega. The light coming out from X in a direction omega is 1 over pi r squared, that's the area factor, times the sum of the bidirectional reflection function at X for light coming in, say, in omega I and going out in omega. They may be in the opposite order in the book. I think they are. It doesn't matter because this is because of reciprocity. Times the flux delta. Did I write upside down delta or delta here? Delta. So each photon has a flux. They may all be equal if you've done them that way. Of that photon. So the positions were needed to figure out what this is, say, I equals 1 to n, where these n photons are, in order to get them close to the point X. And then if it's a diffuse surface, this is constant. But you can, because we saved the photons' incoming directions, if we bothered to, if we want to render a specular surface or a surface that isn't perfectly diffuse, where this BRDF isn't constant, we can use their directions also in this BRDF thing. So if it were constant, then the diffuse reflectivity would be part of this constant. And so this gives you the ones going out in this new direction, omega, in terms of all the omega i's stored with each photon and the power stored with each photon. So it really is flux per unit area. And because it's a BRDF, it accounts for per unit area normal to the beam. Okay, so how are we actually going to use this? There's a proposal in the book which is very similar to the proposal I gave 2 classes ago when I was talking about the Chen paper of combining a bunch of different methods, where he proposed using something like a caustic photon map for certain of the paths. So let's see if I can list the path that you would use. So first you have LS star E. Right? This is a direct or mirror reflection view of the light source. And so you're going to do that with, say, weighted, I should use probably capital, ray tracing from the eye. Okay, and then let me just put DE. This would be direct illumination sampling. Right, that you can do without too much noise, as you've discovered in your homework. The direct illumination, you could get a reasonable picture with the same number of samples with less noise than the indirect, because you're only aiming them at the light source, and it's just shadow rays. Okay, and now 3L S squared S star, probably it should be S plus, right? Because that's what the caustic map has. Just use caustic map. And 4 is going to be L, S, or D. This is one option. If you did this, like this would just say use the global map directly. If you did that, you'd actually, I guess, get some double counting, right? Because you're counting these guys and in the same place you're counting here. So what you'd have to do, I guess, if you were going to do it that way, is make the see, are you getting double counting? Yes, you are. So that wouldn't be a good thing to do. But there might be a way to say, in the diffuse map, we're going to not record anything that came directly from, in other words, don't start recording the photons till after their first bounce, right? Then on a diffuse surface, then this would be always 2 or more Ds. Question?
If you do record photons even on their first bounce, then would you be able to get rid of number 2 and not have to actually do the direct?
You could, but the advantage of the caustic photon map is that usually you have like small mirrors, curved, shiny surfaces. Small part of the solid angle is viewed from the light source. So you can afford to to send many more rays just at that surface per solid angle from the light source, because it represents a small part of what the light source sees. So, And you need lots, not because they get concentrated in ways that change rapidly on each diffuse surface. So it's just a way of using them more efficiently to have a separate caustic map. Again, the caustic map isn't great for penumbras, right? Its real purpose is, yeah, you could. I mean, it becomes more like bidirectional.
I'm not asking about the caustic. I was asking, you were saying that for number 4, that you shouldn't record the first bounce because then you double count it with direct elimination.
Yeah. Because I'm going to cross this line out and say I don't like to do it that way. I'm trying to say reasons why this isn't good. And the main reason is because you can't afford as many photons. It's going to be noisy unless you had a tremendous number. You know, if any of you have tried to avoid the direct illumination with tracing your eye rays until they maybe hit a light source just randomly, you know that's very noisy. So I think it's the same reason. So I'm going to change this. What I'm going to say is we're going to hit a diffuse surface, and then we're going to hit another diffuse surface, and finally we're going to get the eye. Oh, actually we can have more S stars here, I guess, if we want to have all possibilities. So this much would be widted ray tracing. And this would be Monte Carlo ray tracing. In fact, you could put Monte Carlo ray tracing could actually get all your reflections too. I mean, that's probably the way you organize your homework if you put any shiny surfaces in it, which wasn't a requirement. So why don't we just say all this is just like in Chen's paper. We do Monte Carlo ray tracing to the first bounce, but instead of doing a radiosity solution for this part, which is what Chen did with his extended form factors, we'll do the global photon map here. That's not a very good. Okay, and since for the same reason that Chen's paper worked is not showing you the blocky Mach bands or constant radiosity cells on your surfaces, this will not need. See, what's going to happen if you visualize a photon map directly and there are not enough photons? It's sort of going to be blotchy, right? Because your density has a certain variance to it. And even this estimate of how to do the density is going to be denser in some regions than others. And as these spheres move across the surface, as you're shading it, it's going to change slowly. It's not like the noise you've gotten from your actual ray sampling, because you're gathering in each sphere about 100 rays, 100 photons. It's going to change slowly, so it's going to be blotchy, sort of ripply noise rather than the salt and pepper noise that you get from every pixel has a different kind of shading on it. But the principle, so we've got 3 kinds of noise. The salt and pepper noise, the slowly varying map density estimation noise, and then the, it is noise. And the blockiness from the radiosity solution. But no matter what the problem is, gathering them by a separate gather can eventually make that noise go away. So if you trace enough rays at every pixel, then you can when you hit the photon map, it doesn't matter if it was a little bit ripply in color, because you're only using those rays to get the final color of the surface, which is going to see the whole wall. Doesn't care about the individual little ripples on it, because that's not what's being shaded. So this is the way that the book proposes to use photon mapping. Presumably it's the way Henrik von Jensen proposed also. And so the same argument we got last time. This one has all the paths with no diffuse reflection. These two have all possible paths. Actually, probably what I need to do is put an S star here too. I guess with weighted ray tracing. Does that get me all paths? No, I need S star here, right? So this is also with weighted ray tracing. Now I really do have all the paths with a single D. And then, because I put two Ds here before this does represent all the paths with two or more Ds, right? Or more is by these factors. And anytime you have two Ds, you know, you put the two Ds here, and here's all the possible other stuff. That would be all. Every one of those is somewhere in this list. So that's the way to gather the photon map. Okay, so now I can start on the volumes. So photon mapping wasn't really in the syllabus, but I want to do the same thing, shooting rays into volumes. So I'm not going to finish this today. I'll probably continue next time. But what I want to think about for a physical model is some sort of cylinder here with a certain width that I'm going to call ds and a certain area A. And I'm going to look at a bunch of little particles in here, like smoke particles. So this is for what we call a participating medium, participating medium, or in plural media. And that is stuff like hazy air or clouds or smoke, flame, anything that the light doesn't go straight through. Because before we were saying any light that bounced off this wall would hit that ceiling with undiminished radiance. That was this constancy of radiance. But if there's smoke in the room, that's not true. Some of the smoke is going to be absorbed by the particles. Or maybe it's going to be reflected or refracted off of its track by the particles. So we want to figure out how much gets absorbed. If light is going through here and goes through this thickness dr and comes out, how much of it is left? Okay, so I'm going to assume particles of radius r move this r over a little bit, of density n per unit volume. Right, so this n says how dense the smoke is, and this says how big each particle is. And so if we look at the total projected area normal to the beam, which is, say, normal to this surface A, the expected projected area is n per unit volume times the volume, which is A times ds, times pi r squared, the projected area normal to the beam of each of these particles. And so if it hits a particle, it doesn't go through. Now, this is the total projected area, assuming that, you know, this projected area, if these things are so close to each other that this circle and that circle actually overlap, so that when we view it, say, from the point of view of looking straight normal to A, these areas of these particles overlap. That's not going to be true. This is just an upper limit. But the idea is, if you make the slab thin enough, then the chance of overlap goes to 0 basically of order the square of the probability of finding a particle in any position, because you've got to find 2 there. Whereas the density of this projected area only goes to 0 proportional to this thickness. So eventually, if you make the slab thin enough, you can neglect the overlap and just assume, and we're going to take the limit as ds goes to 0. So we'll just assume then there is no overlap. Okay, so let's now look at this projected area fraction. What is the fraction of the total area of this that this projected area is? So basically, we just have to divide by the total area. So we can say the occluded fraction, say. Of the area is, what did I have? NA dr times pi r squared. This was my ds, right? Over a. So the a's cancel. And so it's n times pi r squared times ds. And this quantity is called tau. And it's called the extinction coefficient. And that represents the fraction of the light that doesn't get through after it's but you have to multiply it by a ds to actually get that fraction. You have to multiply it by some small thickness, because the amount that's absorbed is proportional to that thickness. So tau is the extinction coefficient. And that means the fraction that gets through is 1 minus tau. Okay, and let's see. No, let me call it something else. I don't want to call it tau, because tau I want to call for transparency. So the proper definition is sigma t. I was looking ahead in my notes. Or I was thinking ahead and without looking in my notes. That's the problem. This is called, this is sigma is for the extinction coefficient. And now what we want to find is the transparency of a finite segment instead of an infinitesimal length of a ray. So the ray has a starting point, and I want to know the transparency, say, from the starting point x0 to some x. And so I have the ray starting at x0, and s represents the distance along the ray. And basically, I can think of transparency, if s is the distance up to x. I can think of computing tau at each s, the transparency from x0 up to any given length. And I want to write a differential equation for it. And so I want to say tau, whatever it was at the front of this slab, if we look at the transparency at the back of the slab, is the amount that got to the front of the slab of the original light that started flowing times the probability of getting through the slab, which is 1 minus tau at that sigma t at that position times ds. Right? Because this was the fraction that was removed from the ray by being absorbed or bounced or reflected or refracted or whatever. It didn't get straight through. And so this fraction of the original light got to the front of the slab, and then we multiply it by the fraction of that actually got through the slab. And so this is like deriving a differential equation. Because if we multiply this through, this is tau of s minus sigma t tau of s ds. And then we can subtract this from both sides, tau of s plus ds minus tau of s. That's the actual amount that was absorbed, is the transparency up, well, why don't I put it just minus sigma t, and that could depend on s also, if it wasn't constant smoke density, times tau of s ds. And that means now if I divide by ds, tau of s plus ds minus tau of s divided by ds equals minus sigma t of s tau of s. And we can think of this as d tau ds in the limit as ds goes to 0. I said I was going to take a limit when ds goes to 0 eventually, so I didn't care about the overlap. Okay, so this is a differential equation for the total transparency up to a given point on the ray. So now, do you remember anything about differential equations? How do you solve such a differential equation? So the way I was taught is to just put the taus all on one side and the ds on the other side. So I'm going to multiply back through by ds, and I'll get d tau of s. But I'm going to divide by tau of s equals minus sigma t of s times ds. And so that's another way of writing the differential equation. So do you know how to, you need the antiderivative of both sides now to get a solution. So does this look familiar? What's something whose derivative is this? Well, you have to remember your calculus. If you take log n of tau of s, by the chain rule, it's going to be the derivative of the log of tau, which is 1 over tau. That's the part of calculus you have to remember. Does that sound familiar? Times the derivative of what's inside, which is, you know, this part. And what's something on this side, we're just going to go from s equals, say, 0. The light started at point x0 at full intensity. We want to know what fraction got through the distance s. So we're integrating up to s of, say, I'm going to put the minus in front of the whole integral, sigma t of u du. Right? I'm just integrating this, both sides. Okay, and now I'm going to take the exponential. Well, actually, whenever I do this, I have to add a constant, right? Constant of integration. So now this says tau of s equals the exponential of minus the integral from 0 to s of sigma t it's going to be times the exponential of c, right? Because when you take exponential of a sum, you end up with products. And I guess I need to put the parentheses here if I'm putting xc separately. So this is a constant of integration. What is the way to find that constant is what happens at s equals 0. Right? At s equals 0, we're going to have full transparency because we didn't go through any smoke yet. And this integral is going to be 0, so we're going to have e to the 0 is 1. And that means this thing has got to be 1 also in order to get 1 on this side, all of the light. So we can now take this factor away because it's equal to 1. So this is the total transparency, and it makes sense that it's exponential if you have one hunk of smoke or you know, hazy glass or whatever in front of another one. Say it's a filter that filters, one filter filters out 10% of the light, and another filter filters out another 10%. We're going to get, you know, 0.81 of the light left. The transparencies multiply. So 0.9 times 0.9. So this at least gets us what is the transparency through a given region. And one thing I should mention is what happens if you take the same number of particles, I mean the same say, weight of water per unit volume, the same, you know, water content of the air, and make it into smaller drops, right? Then say you make the drop half the size. So R squared is going to be a quarter. But the number of particles is going to be 8 times as many, right? Because the original volume that was in one particle nails into 8. So this quantity is actually going to double. So the smaller you make a given mass of particles per unit volume, the greater extinction you're going to get. So let's see, what do I have time to talk about? Don't have time to talk about surface radiance. I can talk about emission. Suppose these particles are actually glowing, like they're hot soot particles in a flame, right? Then the fraction that you're looking at the stuff behind this slab, what you're going to see for the fraction that isn't getting through, you're going to see the color of the glow. And that's going to show up as volume emission. And so what's happening is we are going to, into this differential equation, we have this much is subtracted per unit length, but we also have sigma t times the color of the glow. Right? So this thing is what the book calls the emission. And basically what you can think of is these particles are emitting a certain flux of energy per unit volume. And the emission along any given direction, if you think about it as this emission, the volume emission, and at this position is radiating out equally in all directions over the whole 4 pi hemisphere. So the amount that's coming into an array in any given direction is 1 over 4 pi times that total radiation in all directions. And that's what you add into here. And that affects the differential equation. So next time we'll have to see about how we can get an answer if there is volume emission coming into the ray, and also if there's scattering coming into the ray, because if we have light coming from other directions, they could bounce off this particle and come toward your eye. And so we're going to study scattering the next time also. And we'll get an equation which takes care of the inscattering as well as the modification for the emission that I've just given you. And then we'll use that to somehow do a sort of a Monte Carlo scattering of particles from light sources inside the volume and build a photon map that way. So that's the goal for next time.